Hey everybody, it is Yishan here. The title is not clickbait. Today I am going to teach you how to calculate your tier element meal probabilities in 5 seconds. And not only that, I'm going to show you how I came up with a mathematical process to come to be able to calculate these probabilities for you. So you are going to be a better player at the end of this video. And in fact, sometimes these probabilities don't even just apply to tier elements, although they'll apply best to tier elements, and I'll sort of explain why that is the case, right? So let's first talk about how probabilities are usually calculated, okay? Probabilities are usually calculated following the hypergeometric distribution. Now, that's a lot of fancy words. All that really means is that you have a sample, which is your deck, right? You have some successes, some cards you're trying to draw, and the rest of the cards are fails, right? So the card is either a success or a fail, and you don't replace the cards that you draw, right? So that's just technical speak for what a hypergeometric distribution is. And these are really great, and you can do a lot of calculations, right? You can find the calculators online, do the calculations yourself. There's a lot of great programs out there. But the problem is these calculations are difficult to do in your head. As you can see here, we've got a very complicated formula in here with all these chooses and multiplies and divides. Not for me, right? Not for me during the game. I just can't do that in my head, and I can't do these calculations in a game. And so I thought, is there a way I could teach you guys how to calculate these probabilities in a game in 5 seconds so you don't get a slow play warning? And the answer is, actually, turns out there is a way. So let's talk about what you're going to learn in this video, right? So these are the kind of questions you are going to be able to answer after you're done watching, right? Let's suppose you're in a scenario where you have a tier elements haveness. Its effect mills 3 cards, right? And you have 25 cards left in your deck, and you have 6 tier cards that you want to hit. What are the chances you mill at least 1 tier element card? Well, this is not a complicated question to answer if you can just go online and search it up, right? You can plug all that stuff in to a hypergeometric probability calculator. Boom, you're done, right? You get the answer. But we want to calculate this in our heads. We want to be able to calculate this in this match of Yugioh where we don't get a slow play warning. And so we're going to calculate this by estimating the probability. And well, how are we going to do that, right? Well, the first thing we've got to do before we do anything is we need to narrow down our things that we're estimating, right? We don't want to estimate the entire hypergeometric probability distribution. You know, those numbers go from 0 to infinity. Instead, we say, okay, well, you know what? The tiers left in our deck, there'll probably be probably around 2 in 10 of them. This is actually, if you're a programmer, this is technically 2 in 9 because ranges are not inclusive. That's just, let's just make it simple, right? Between 2 and 10 of them. The cards left in deck, I always say there's probably going to be around 10 and 35 of them left in your deck, right? And the number of cards you mill, usually somewhere between 3 and 10, right? So, okay, we've narrowed down our space from infinity, from infinitely large to something maybe a little bit more manageable, right? We can calculate all these probabilities with code, right? It's just easy to loop through all these and calculate the probabilities. So what do we do next, right? That's sort of what I did. I went through and I calculated every single probability in our space, right? And actually, I find that I'm a pretty visual person, so I want to take a cut right now and show you what exactly that looks like when it's graphed out. So let's take a look at that. Okay, so as you can see here, we have a graph. Now, what in the world are we looking at? Well, we're actually looking at a 3-dimensional graph here. But how do you graph something that's actually 4-dimensional, right? We have our tiers in deck, our cards in deck, and our number of mills. How do we even graph something that's 4-dimensional? Well, we plot them as colors. So the points have values themselves, right? And you can see the more yellow they are, the more closer to 100% you are to be able to mill a tier card. The closer to purple they are, the less likely you are to be able to mill a tier card. Now, I sort of want to show you, I'm going to move this around. The great thing about programming is you can sort of move this around. You can take a look at it. I want to show you something over here. You see in the top right corner over here, we can see here that the number of tiers in deck is going to be 9, right? And the number of cards in deck is going to be minus 20 is going to be really, really small, right? So once it gets past a certain point, the graph actually stops plotting points because you're guaranteed to mill a tier, right? So maybe around, you know, when you're milling 9 cards and you have 9 tiers in deck, when you start milling, when you mill 10 cards, right, you're guaranteed to hit a tier. So this is sort of what this probability distribution looks like. This is our space, right? And, you know, this is calculated using the hypergeometric formula. but we want to make it simpler for you. We want to be able to help you estimate the probability, sort of the value of these points, as long as you know these three numbers: the number of cards you're going to mill, the number of cards in your deck, and the number of tiers in your deck, right? And we'll get to this minus 20 later. What does that mean, Yishan? But that's what we're trying to estimate here. So I wanted to give you a little visual before we go back to our PowerPoint. So let's go back to the PowerPoint and let's take a look and see what comes up next. So we took a look at the graph, right? Now what I want to do is I want to write something simple. I want to say, hey, you know what? I want to do simple math. I don't want to do all that complicated probability math. I want to do some simple math, and I want to try to minimize the error. And what does that mean, right? What do I mean by minimizing the error, right? Well, basically I'm saying, hey, whatever probability we're going to guess, it's not going to be perfect, but I want it to be as close to the real probability as possible. Now I have this picture down here. I don't know if you remember, maybe in middle school or in high school, you did these things called lines of best fit, where basically you had some points on a graph, and you try to draw a line through all of them and to make them as close as possible. And that's exactly what we're doing here. We just have more dimensions, more variables, right? And so I said, okay, you know what, guys? I think we can multiply three numbers and add them together, right? So I said, okay, we're going to multiply the number of our tiers in our deck by some percentage. We're going to multiply the number of cards in our deck times some percentage. And we're going to multiply the number of mills in our deck multiplied by some percentage, right? So luckily, you know, some great people out there have already written code that allows us to easily draw these lines of best fit, or even, you know, you can think of them as like three-dimensional shapes of best fit here. And all I had to do was write a little function that calculated the error, basically, and the function, the program, the code that these gracious people have written for us would actually minimize these three numbers. What are these percentages, these variables, right? It'll pick the best percentages so that when we do this computation, when we multiply and add these numbers together, it'll be as close to the real probability as possible, right? So this is a little coder thing here. I have this greater than 1 and less than 1.5. I just wanted to point that out. What does that mean, just in case you're interested? That means that basically, listen, if the function predicts a value more than 1 or 100%, we know that that's impossible, right? We know that there's no way you could be better than 100% in milling your cards, right? Like there's no way you can be more than 100% likely. So if you're guessing more than 100%, your guess is 100%, right? So that way the error doesn't get too skewed by big numbers. And then I had to do this less than 1.5 because when you know, the optimizer can get a little crazy when, you know, you say, hey, if you ever guess a number greater than 1, you scale it back to 1, it'll start picking gigantic numbers because it has this easy fallback. So I had to make sure that it, you know, don't go too crazy in the big number direction. We want legitimate numbers. So little code side talk there. Okay, so what did I learn along the way? Well, there were a couple issues. One of the issues was that the range of possible values for deck size was really large, right? Larger, you know, went all the way up to 35. And I was like, dang, it makes it hard because that number is so much bigger than the other numbers. The percentage that you're multiplying it by goes way down. And we need like legitimate like percentages. We need like percentages that, you know, 1 or 2%, not 0.13%, right? So we need real percentages. So what I did was I subtracted the deck size by 20, right? I said, okay, well, what if I narrow the range somewhere between like -10 and +15, right? That makes the magnitude of the number smaller. And then sometimes, of course, the estimation function would predict a value greater than 100%. We already talked about this, and I chose to make the function predict a value less than 100%, because obviously, you know, if it predicts more than 100, you know, it can't be greater than 100, right? So little math stuff, but let's talk about the results. This is what we're all here for, right? What did we learn? Well, the best coefficients are these: the 8.17 times the tiers, the -1.96 times the deck size minus 20, and 7.1 times the number of mills. These are what the sort of the probability, the optimizer calculated. Okay, no one is ever going to remember these numbers, right? So what I said is let's just simplify it, right? Let's make it 8, -2, and 7. Boom, done, right? We can remember three numbers. And you know what? I calculated the average error, and it's only 3.53%, whereas the average error of the optimal numbers is 3.32%. So we're actually only losing 0.2% of our guessing power, and we have easier numbers to remember. So what does this mean? Let's see it in action. Let's see these results in action, right? Let's test it out. So remember our original question. We had 6 tiers in our deck. We had 3 mills, and we have 25 cards in deck, right? That's our Happiness milling 3 cards. Well, we take 6 and multiply it by 8, right? Number of tiers times 8. Okay, that's 48, right? The number of mills times 7. So 3 times 7, 21. And then the number of cards in our deck minus 20. So 25 minus 20 is 5 times -2 is -10, right? So we say 48 plus 21 minus 10. What does that equal? 59%. That's our guessed probability, right? And we can do that really quickly. What's the actual probability? 57.87%. So we're only about 1% off, which is mind-boggling, right? This is super, super, super cool. And anyone can do this math. You'll get really good at doing these calculations once you've done them like 4 or 5 times. You just practice a little bit, right? So remember, it's 8 times the number of tiers, 7 times the number of mills, plus -2 times the deck size minus 20. So I said, why don't we just try it out on the fly? I'm going to pick completely random numbers. Okay, so let's start with an easy example, right? If our deck size is exactly 20, then we can sort of ignore the -2 portion, right? And we have 6 tiers in our deck, or you know what? We're going to say we have 3 tiers in our deck, and we're going to mill 8 cards, right? So what is this telling us? We're milling 8 cards, so 8 times 7, 56, right? 3 times 8 is 24. What's 24 plus 56? Quick math, that's 80%. We're always guessing, you know, at least 1 tier. So we should be around, I think 80% is what I said, right? And we calculate 80.7%, right? Okay, what if we made the population size bigger to 25, right? Well, remember, as we go above 20, we have to subtract 2% basically for every card we go above 20. So we should be around 70% is what my formula tells us. What are we around? We're around 70%. What if the cards are below 20? What if there's only, what if there's only 15 cards in our deck? Well, then we're actually adding 10%, right? So remember, our original calculation was 80%, right? But when we subtract 5 cards, you have 2 negatives. You have a -5 and a -2. They sort of, they multiply, and you actually add 10% to your probability. So we had 80%. Now we calculate this. Now we have 92%. So we're actually a little bit off here. We're off about 2.3%. But as you can see, the formula isn't perfect, but it does work pretty freaking well. And I challenge you, just go pause the video, keep that formula in one tab, try out all these calculations, right? Try out what you see here. Let me know how it goes. There's so many different ways to do this, so many different possibilities, but this should make it really, really close. And you can do this yourself on the fly. Check it for yourself. Let me know how it goes. I'm really excited to see how that goes. All right, guys, let's get back to the PowerPoint and wrap things up. So we are back, okay? A couple of things. Always remember a couple things, right? If you put tiers on the bottom of your deck and you haven't shuffled your deck, you know you're not going to mill those tiers, and you also know those tiers aren't really going to be randomly distributed in your deck, so they don't count towards your deck size or the number of tiers in your deck. Another tip, if your function estimates a number greater than 100, you know the probability is probably somewhere in the high 90s, okay? Thank you guys so much for watching. I love making these math and Yu-Gi-Oh videos. I hope you guys learned something interesting. If you enjoyed them, they do take a lot of work to make. I would really appreciate it if you subscribed. Check out my TCG player and your playmat links. If you have any questions, please let me know in the comments below. I tried to make this quick and concise, but not bogged down with too many details, but also explain a little bit. But if there's anything unclear, let me know. Did I make a mistake? Very possible that I made a mistake in this. The stuff, I do it all by myself. So, let me know where you think the mistake is. I'll try to pin or heart your comment with an explanation if either you're right or you're wrong, or if we agree or disagree. Other than that, guys, thank you so much for watching. I enjoy making this video for you. I hope it helps you in your gameplay. That's all I got for this time, guys. I'll see you guys in the next video.